Hello, everyone. Thank you for tuning in. My name is Eric Peterson, and I'm going to be reporting on a software package, aether, that I developed with my colleague Peter Karalekas, which focuses on the emulation of distributed systems. Um, Peter and I were motivated to work on this project by a very particular application, and I wanted to share that with you because it will help motivate some of the internal structure of the package once we get there. So Peter and I have both been working in and around quantum computing for some years now, which is the domain where you'll find our application. You don't need to have any background at all in quantum computing to appreciate this talk. I'm going to tell you about the parts that are relevant. The place to start is to note that quantum computers come in two pieces. There is the part that's pictured on the right of the slide, which is a really elaborate physics experiment. The part that is like most interestingly quantum mechanical sits down there at the very, very, very bottom. That little flat gold cylinder, sometimes called a puck, that's where all the magic takes place. And the rest of the apparatus on the right is a bunch of wires and shielding that is meant to deliver some very specific intentional radio signals down to the puck, and otherwise shield out all kinds of noise, thermal and radio and so on, to keep that from interfering with the computation. But on its own, if you just have this thing sitting in your living room, it doesn't really do anything. It just sits there. In order to make this thing do some interesting computation, you have to drive it with some other computer that actually feeds those intentional radio signals in. So associated with the quantum part of the quantum computer, there's a family of classical computers pictured on the left that are responsible for driving the individual radio lines. So they communicate with one another over network interfaces, and then all of those gold coax nubs that you see pictured are the things that connect to those looping wires that proceed down the chandelier. And so their job is to coordinate with one another in order to figure out which radio signals are worth sending and why. Like all computers, quantum computers also experience noise and errors at the hardware level. And so in order to correctly perform a quantum computation, there has to be some kind of error correction procedure where these errors are noticed and counterbalanced. This is really tricky in the domain of quantum computation because you may have heard this trope about Schrodinger's cat. It's this being that's both alive and dead at the same time in some kind of superposition state. But when some classical observer finally looks at it, the cat is only alive or only dead. And the moral of this story is supposed to be that even if quantum mechanics allows for these fantastical states that we're hoping to exploit to do fancy computation, if a classical observer ever looks at it, then those quantum states collapse just into classical ones, and you lose the computational power that you were hoping to exercise. And this is really uncomfortable from the perspective of someone who's been charged with error correction, because surely in order to correct an error, you have to be able to identify it by inspecting it so that you know what kind of counterbalance you're supposed to inject. So a lot of theory and engineering work has gone into this problem already, and people have arrived at the following scenario, where a quantum error that occurs inside of the machine one can think of as a family of snakes laid out on some family of qubits. So here a grid. And so this is internally what the errors look like. What the electronics get to hear about as sort of the signature of the error isn't the exact picture of snakes involved, but just the positions of the heads and the tails, which is quite a lot of information, but it's not all the information. So if somebody just tells you the head and the tail position of a snake and tells you that your task is to reconstruct the snake in order to cancel it out, you can draw lots of different snakes, like any kind of zigzag that you can think of, that connects some head to some tail, and that'll satisfy the condition of being a snake, and it's impossible to tell if it's the snake that you started with. So the other miraculous theoretical feat that's in play here is that the error correcting procedure is designed to be robust to only approximately coming up with the pattern of the same underlying pattern of snakes. So if you're able to design some pattern of snakes and it's not too far off from the true one, then it will still serve to correct the underlying quantum error. So here's a picture of a reassembled family of snake heads and tails. It doesn't match the one that we had originally back in the cyan slide, but it turns out that this satisfies the good enough condition. So this guy, Austin Fowler, proposed a particular mechanism by which this might be done in sort of at the engineering level. So he said that one way that you could address this approximation problem is by trying to draw snakes in a way that you get the shortest family of snakes available, or the least total snake biomass. So more often than not, this satisfies this approximation condition. And so if you can manage to do this, then you're really off to the races. The trouble is that this graph algorithm that you're hoping to run to connect the snakeheads and tails has to run on a fleet of classical computers that looks like that picture on the right. And so you need some kind of distributed graph solver to make this happen. And more than this, we're looking for a couple of really key properties in such a solution. One is that we want it to use bounded resources in the sense that the quantum computer, as it's alive, is going to be constantly throwing us more of these snake patterns. And we want the classical electronics to be able to keep up. We want to be assured that if we just make them sufficiently snappy and we make the network interfaces sufficiently have sufficiently high bandwidth, then these things will be able to solve the decoding problem sufficiently quickly that they don't get bogged down under just a pile of snakes. And a little bit more than this, we would also like this to remain true even as we build very large quantum devices. So as that grid on the previous slide gets really, really large, we would like to just plug more of these classical computers into a network and have them figure it out and coordinate amongst each other without having to bump up all of their processor clocks or something. So Fowler asserted that this should be possible, but didn't actually give an implementation of anything. And if you've worked around, distributed systems in particular, but really any kind of computing, you know that there is often a really enormous gulf between someone saying something will probably work and an honest-to-God implementation of it. And so what we wanted to do was probe these particular constraints. So we wanted to make precise exactly what was going on in Fowler's proposal and turn it into something that could be implemented. We wanted to simulate its implementation on generic hardware. So we didn't want to get bogged down early on with decisions about what different microprocessors and their architecture should look like. We wanted to run it on sort of quote-unquote generic hardware in order to verify the qualitative claim that if we just made everything in the picture snappy enough, that we could keep up with the snake handling. And then once we'd managed to verify that, then we also wanted to probe this intermediate regime where if we knew that it was possible with extremely snappy electronics, and we knew that it's not possible if you have really dull electronics, then somewhere in the middle is some kind of threshold where if it's faster than this point, then you can do it. It's just keeping up. And so if you're slower than this point, then you can't. And that could come from a bunch of different places. The processor clock rates might play a role. The network bandwidth, the network connectivity, latency, all of these things might sort of influence the tipping point of exactly what makes this problem solvable. And so we wanted to explore those precise cutoffs because they're super important when you're trying to engineer a quantum computer. So aether is the arm of this project that just concerns the simulation. The other arms we hope to release in the near future, but for now, and in this venue, we're just going to focus on the simulation. So aether comes in three interleaved components. The bedrock part is a framework for the simulation of time domain events. So the kinds of things that you should imagine an event to be is an update of a particular microprocessor. But if we're in the scenario where we may have a whole host of microprocessors, they may not be uniform. There might be different kinds. They might have different instruction sets. They might have different clock rates. They will definitely be running different programs. And we wanted some kind of user-friendly system that will make it very easy to have a whole different host of those things all compatibly simulated in time order. The next thing that we wanted on top of that was some kind of networking layer that allows the kind of simulation that we were talking about on the previous slide. So aether provides two kinds of networking layers. There's a physical layer constructed out of these things that we call couriers that are responsible for the actual transmission of packets from one network interface to another. And so this is the layer where you can expect to find things like congestion or different routing algorithms or latency, delivery latency encoded. But then on top of that, we didn't want user application software to have to necessarily directly touch these network interfaces. And so we provided a logical network layer that was more opaque to all of these details, so that different computational actors on the network, perhaps at different nodes, are able to like seamlessly send one another messages. And then on top of that, we built this actor framework in order to support computation that makes use of this communication layer. So again, I want to encourage you to think of actors as being one of two things. Either an individual actor might describe a particular hardware component, like an individual microprocessor, or again, this is the most valuable in early stages of design. You might have an actor embody a particular like application feature. So you think of this as kind of like a black boxed hardware component whose details you haven't wholly specified. It just has some API that's sending messages and receiving messages with other components in the network. And eventually, you probably intend to boil that down to a program that's running on some simulated microcontroller. But if you don't want to deal with that immediately, you could just simulate the application behavior. So this is a lot to take in, and I wanted to help you digest some of it by going through a small example. The one that we're going to work through is using a distributed algorithm to color a line of nodes, so a linear graph, with 3 colors. So this is something that you can do immediately, classically, if you know the like array index of each of the nodes on the line. But if the only information that a node has is an ability to like chat with its neighbors, then sequentially, it takes a long time to solve this problem. But interestingly, there's a distributed version that's quite snappy. And it's also, it's simple, and you get this cute result, and you get some of the flavor of what it's like to program like this. So we're going to define one of these computational actors called a coloring process that inherits from a base class that Aether provides called a process. So our coloring process is aware of 2 bits of information. There's the color that it is assigned to itself, and there's a list of its neighbors, like sort of on either of its sides in the line. The next thing that we're going to define is the basic unit of communication in this algorithm. So the only communication that has to get done is that an individual coloring process might query one of its neighbors to find out what its neighbor's color is. So Aether again provides one of these base classes called a message that we'll subclass off to build a message color query. We'll also define a handler so that when a coloring process receives one of these color query messages, it looks up its color slot and replies with that value. And then we'll also link these two together. So we define this dispatch table so that when a coloring process receives a message of color query type, it invokes this handler that we defined in the previous form. Then we start working on the computational stuff. So the computational state of an actor in Aether's framework is modeled by a stack of continuations that have yet to be computed. So the stack always starts with the start token on it, and then we define 2 more states that the process could be in. So there's this query state, which is where the bulk of the computation is going to get done. And the job of the start continuation is just to push the query continuation onto the continuation stack and then move to it. And then there's also this idle state, whose job is just to like busy wait in the idle state, where the idea is that this will keep the actor from terminating so that it's still alive to receive and reply to messages that are inbound. And so here's the body of the query continuation. What it does is it randomly picks a color to assign to itself. Then it sends these color query messages to its neighbors, and then it performs a blocking receive, waiting for them to get back to it. And then things fall into one of 2 situations. Either this color that we were just randomly picked overlaps with the colors of our neighbors, in which case this is not a legal solution. We should try again. So we push the query continuation back onto the continuation stack and finish this bit of computation. Or if we don't overlap, then we know that it is possible to solve the coloring problem using this color. And so we say that we're done doing any kind of computation, and we drop into the idle state. So that sets up all of the actor behavior, but it is shy of actually extracting runtime properties from it. If we wanted to simulate this, then we have to set up a simulation. So I wanted to also walk you through that. So the first thing that we do is we pick a number of nodes that we're going to put on our line. The next thing that we do is we set up some of the Lisp objects that are underlying these simulation components. So for instance, we build the simulation object and all the different courier objects, which I've suppressed from the example because they just look like a bunch of calls to make simulation and make courier and so on. The first interesting thing that we do is we have to inform the simulation that it's responsible for requesting updates from these different objects. So we loop across the different couriers, and then we poke them one at a time into the simulation. The next thing that we do is we associated to each of these network interfaces that are again all in a line. We build we also construct one of these coloring actors. So we do this by first specializing to the jth network interface. We bind this dynamic variable local courier that says that this is the network interface against which we're operating. And then we spawn one of the coloring processes which automatically gets associated with that local courier, and we poke it into the simulation. And there's a bit more work here where, for instance, I have to go and loop back and inform each node of its neighbor's logical addresses so that it knows where to send messages. More interestingly, I also have to set up a stopping condition. So my stopping condition is going to be when all of the coloring processes have fallen into the idle state. And then I'm going to declare the algorithm done. And with that in place, I can then run the simulation and process these continuations until I meet the termination condition. And once that happens, I can inspect the horizon slot of the simulation because that'll tell me the stopping time, the amount of time that it took to run the whole algorithm to completion. And then maybe I'll wrap this whole thing in some kind of statistical average loop to get some expected runtimes out and see what happens. And you can see the output in the bottom right-hand corner of the slide. If I run this algorithm for 4 nodes, then it takes about 9 ticks in simulation time, not in wall time. And if I color 8 nodes, then it takes about 14 ticks, 16 nodes, 20 ticks, and so on. The thing that you should notice is that even though we are exponentially increasing the number of nodes that are in the simulation, the amount of simulated time that it takes for the distributed algorithm to complete only suffers a linear increase. And so this is supposed to be the punchline for why anybody bothers with distributed computing. You can solve these problems that only involve quote-unquote local information more efficiently than you would be able to if you attempted a sequential approach. So in our intended application, we are pursuing something considerably more complicated than just 3 coloring a line. And a complicated algorithm means a lot of surface area for bugs. And so the majority of the features in Aether are centered around helping the application designer debug the kinds of problems that come up in practice. And the good news is that because we're working in Common Lisp, we sort of already have a real leg up on this scenario. So Common Lisp comes with a really nice debugging system. So there's sort of the live Lisp image itself, together with Swank and Slime, is a really powerful collection of tools. It lets you directly manipulate the state of everything involved, which is particularly convenient when the entire state of this ensemble of distributed computers all lives locally on your single monolithic computer. So this already puts you in a really good position. Unfortunately, it is insufficient. There are some wrinkles to distributed programming that just aren't totally well served by this scenario. So the first, really, in my view, critical tool that Aether provides is a logging stream for events within the distributed system that's programmatically searchable. So if you know, for instance, a particular message ID, you can not only sort of extract all the messages from the stream that have something to do with that ID, but you can also look at its knock-on effects. So maybe when it's received at a particular point, it causes that receiving process to generate a bunch of new messages, and you can write this programmatic search to then trace their effects and so on. And then more than that, when you isolate a particular event that you find suspect or interesting, you can zoom out from it in time order, so that you look at events that are happening around the same time across the entire system, so that you can see if there's something like a race condition in play. Um, there's also an opacity breaking mechanism that is extremely helpful. Processes in Ether never directly touch each other's underlying Lisp objects. They only interact with one another by sending each other messages over the logical networking layer to logical network addresses. And this is really great for encapsulation and keeping the application author from smearing bad state all over the place. It's also really inconvenient from the perspective of debugging because it's often difficult to tell exactly who is supposed to be receiving a message, whether you're sending it to the correct place that you think you are. And so Ether provides a debugging mechanism for breaking this opacity, which is really a boon. And then, of course, because you have access to all of the simulation guts, you have the ability to do things like hand inject new events or play with the latencies of things in order to manufacture race conditions to explore whether they're a problem. The other really featureful part of Ether, again, harkening back to the application that we're after, is a whole bunch of instrumentation features. So we're interested in a bunch of different runtime properties of an algorithm in practice. And those include things like its network usage, or how computationally intensive the family of distributed computers finds it, or the overall runtime, et cetera, et cetera. And so some things that some examples of things that one might mean by this are counting the number of live messages in the system, or counting messages of a particular type that have ever been transmitted since the dawn of time, inspecting network congestion by looking at the queue depth of any particular physical courier, or looking at how often a particular network interface has a message cross over it. Or on the more computational side, you might look at the number of live processes or the number of processes that are live, and also not presently in a blocked state as they're waiting for a message receive, or how often a particular continuation or actor command gets invoked, and so on and so forth. So on the right-hand half of the slide, there is an example illustration of the interface use instrumentation portrayed. So cool colors in this picture correspond to little use, and warm colors up in the reds correspond to high use. And you can see some global structure in the picture, that in the corners there seems to be very little use, steadily increasing towards the middle, except also for some particular high usage strips in the centers of the edges. That corresponds to the particular packet routing algorithm that we were using. And a different choice of algorithm would result in a different global structure. Maybe more interestingly, though, you can also see some fine structure. If you look in the middle of this picture, there's a row of hot red arrows. That actually corresponds to a crash that occurred in the software that's being simulated. So at the source end of that trail of arrows is some crashed process, or some process that's gotten into a bad state that is just endlessly sending messages to some target further to the left. And that's called, you can see that reflected in this usage graph. Here's some other examples of similar instrumentation statistics that one can extract. You can see how often couriers are responsible for sending messages. And again, there's mostly uniform global structure, except for a couple of questionable strips that correspond to bugs in the software that's being simulated. You can see how often couriers are meant to be the destination of messages. Again, some interesting anomalies. And then you can also see where congestion is happening, that by studying the average number of messages that are pending to be processed by one of these physical layers. This isn't a totally exhaustive set of things that could be extracted, but I hope that it gives you a sense of the kinds of problems that you're able to study with these kinds of tools. Thank you very much for your attention. It was, again, a pleasure to be asked to speak at this, and it was also a real pleasure to work on this project. It's a really, really interesting problem in a really interesting field. You can find this package on QuickLisp. You can also find it at this GitHub address. And you can find me on IRC right now, answering your questions during Q&A. Thank you very much.